This is one of those talks that I think will go into maybe even the history of AI, but definitely in the sort of shorter term history. It's reinforcement learning with large data sets. Sergei Levine gave a talk at Winter AI workshop. I put the link. I don't know exactly where it was. Doesn't matter. So this talk is really, really fundamental. I think huge kudos to Sergei. He's always been inspirational, but this talk, I think, will change the course of embodied intelligence. This episode is part of the Foundation Models for Embodied Decision-Making Agents series. So this is episode 11, but it's also generally just a conversation about some really fundamental ideas that Sergei is bringing up. So the idea is that we combine data-driven AI with optimization. In other words, we have the sort of maximum likelihood driven statistical techniques that are incredibly successful in transformer technology, large language models, and even before that, let's say convolutional neural nets, ResNets. All these models are in principle doing the same thing. They're trying to match a certain input to a certain data distribution. So we're trying to match, okay, this particular piece of information fits really well into, let's say, that particular distribution. So this is a cat, this is a dog. This word fits really well into the sentence. I'm walking on the beach versus I'm walking on the ladder is not such a good choice. So we have these probabilistic models. That's what data-driven AI kind of is. Reinforcement learning is optimization. Reinforcement learning is the idea that we can find better trajectories from A to B, whether it's in actual embodied environments where a robot literally has to go from A to B, or a car, or it's a text bot that is supposed to answer the best possible answer to a question. How can I relieve my depression when the weather is really bad, or whatever it may be? All these ideas, all these bot type situations, or robots like embodied decision-making agents can be improved with RL. So what Sergei is trying to do is combine those two. He's trying to combine, he's saying, why don't we use the best of the data-driven AI world and also combine it with RL? They're complementary, and maybe we can get to something like Move 37, which is a metaphor for a machine-driven, a sort of hermetic, on its own rules learned type of situation, and it comes from the AlphaGo Zero event. For people who aren't familiar with that, I don't want to spend too much time, but AlphaGo Zero was trained on its own through self-play in a pure Q learning type setting. So it was hermetically sealed. It learned self-referentially on its own data, on its own type. It was, though, of course, programmed through a reward function by humans, but still, there was nothing more than scale data and simulation, and then there was some explicit programming. In particular, the reward functions had to be programmed by humans, but other than that, there was nothing else. And then they came up with Move 37, which is a creative move that nobody would have expected. In other words, humans wouldn't have done this. And the same happened in Davide Scaramuzza's work with the drones. There, the drone took a trajectory that a human wouldn't have chosen. And I'm going to discuss this actually towards the end of this episode, because there's a question about reinforcement learning with human feedback. And some people are saying, well, we don't need that. We can have the machines come up with their own stuff. But I'm not so sure. We probably still want to keep human feedback in there just to make sure that the machines do what we would like to do. But the main idea of Sergei's presentation is, how can we build a Robinson Crusoe robot, or a robot that can be sent to Mars and figure stuff out up there on its own? Like, how can imagine you drop a robot on a deserted island, you give it some resources, and then you come back 2 years later and you find the robot has built a shade to protect itself from the sun. It's built electricity harnessing methodologies to recharge its batteries, and maybe has some stuff for fun. Imagine something like that. So this would be really amazing. Now, the outline of this episode is a recap of the talk. Sergei talks about offline reinforcement learning. He then talks about applications to robotics through foundation models. So how can foundation models be used in robotics? Then reinforcement learning with generative models. So what that means is how can reinforcement learning be used to improve, let's say, diffusion models? And then lastly, he's talking about how offline RL can help large language models. And just to be clear, in the latter two, the idea is how can we improve the actual model? So the diffusion model is a statistical inference from a data distribution, and how can we use reinforcement learning to improve that particular outcome? And the goal of reinforcement learning is always the same. It's outcome driven, right? It's like, okay, how can I get a better outcome? It might, and also, how can I get an outcome that might not be represented in the data distribution? So for example, in the reinforcement learning generative models, how can I get a dolphin riding a bike? This is something that the model has never seen in the data distribution, but reinforcement learning can actually get us to this outcome. This is an Even Long podcast. It's March 29, 2024. This is Krim Delco. It's the end of the first quarter. For the quarter, we're down 16.7%. The market is up 10.1%. We're underperforming by 27.7%. Just real quick about the quarter, it's been a tough quarter for us because Tesla has actually from the get-go started trading down. In the beginning, it was with the market, and then the news started trickling in, pricing actions, and then the earnings call. It actually started well with delivery numbers. The delivery numbers were pretty good on January 2nd. But everything else, unfortunately, was negative. The main problem with Tesla is that they're facing competition, that the competition is coming from the EV space and from the ICE space, that there is an overhang of maybe less enthusiasm towards EVs and less enthusiasm towards electric cars, which could maybe be the same thing in a sense. Less enthusiasm towards EVs and less enthusiasm towards Tesla. And it could be the same thing. That's actually a good question. Maybe the lack of enthusiasm for electric cars just stems from the fact that Tesla dominates the market and people have a problem. Maybe it's political. It's hard to say for us, but what we can say is that Tesla has the best product in the market. It's the best value, and that eventually those things win. We can say that by far, best price, best value, and that's where we stand right now. We have concluded the earnings call towards the end of January as a situation where we expect price stabilization and margin stabilization, at least, maybe less growth, but at least those things have stabilized. And we're also expecting a monetization of Cybertruck and software, in particular FSD, but also other software items. So there could be some growth, maybe mid-teens type earnings growth this year, which of course makes it relatively difficult to justify the stock valuation right now, but we are looking at much, much bigger growth in the latter years. And therefore, we believe that the stock is not exposed to much more downside. We are waiting now for delivery numbers. Of course, things could change. We're in the prediction business here, and we don't have a good sense for what's actually really going on the ground. If we just walk around some of the sales halls here around Silicon Valley, particularly Palo Alto, it's definitely visible that there is a bit less traffic. So that's visible. You don't see the test driving cars, for example, are not used as much. But then on the other hand, service centers are full. People are there's high penetration, of course, but maybe Silicon Valley is also not the best test case, because the penetration here is just really, really high. I think lastly, what I want to say about Tesla, and this is something that I'm working on right now, I think in general, what we see is we see adoption of Tesla as a product, as a design, as a concept, as an idea, as a philosophy, coming from a rising upper middle class from Asia. That's definitely the case. And it reminds us a little bit of the time, of the modern time in the turn of the 20th century, when modern art was really appreciated mostly by Americans and then by Europeans. So why do we draw that comparison? It's because sometimes newness requires a view from the outside. You know, this is a bit quantum. Like, you need an outside observer to actually to observe quantum. To observe something. And in the case of novelty, the incumbents are typically reluctant to accept it. And we see that here in Silicon Valley. You know, the adoption in Silicon Valley is huge. I always use the example of Hong Kong. The market share of Tesla in Hong Kong is in the 30% range. The market share of Tesla in Switzerland is 3%. It's the same demographics, same type of wealth, education, all those things. But we have a much higher, and that's because there is the sensibility of a rising upper middle class in China in particular, but in Asia in general, but mainly in China, coming from a new, go-getting type, demographic that also is very well represented here in Silicon Valley, and those people are jumping on the sensibility that Tesla is providing. That's the good news. That's the future, but we'll see how that translates into sales and margins. Now let's talk about this paper, reinforcement learning with large data sets. So the fundamental idea is we can combine data-driven AI with reinforcement learning, and the motivation is, how can we take advantage of large amounts of data and statistical inference that can be drawn from that data, but also optimize for outcomes. I think this is how I would generalize this talk. And I'm gonna go through the points. So number one, offline reinforcement learning fundamentals. This is mainly centered around the Q function. So the idea is here is you have the choice to take an action, and you're gonna look at the world in the following way. You're gonna say, if given the state that I'm in, I have a choice of action A1, A2, A3, A4, and each action, after the action, I'm gonna follow the same policy until the end, and then maximize my reward. And then I'm gonna choose the particular action that maximizes my reward. Yeah, so I have a certain policy. So for example, I'm just going to do the same thing all the time. I'm going to turn right all the time. And now I'm going to ask myself, if I turn left or right, and then keep turning right for the rest of time, what's my maximum reward? And if turning right gives me a higher reward than turning left, I'm going to turn right. And then in the next instance, I'm going to ask again, right, left, and so on and so forth. Now, this was a simple binary example, but you can think of this as a highly dimensional sort of search space, and Q learning is based on that. Sergei then talks about the conservative Q learning, which is helping to solve outer distribution motivations, which means that what if you start going towards too far away from sort of the optimal trajectory, you could end up in no man's land. So you turn a little bit right, you turn a little bit right, and the next thing you know, you're in the desert and you left the road. So that's conservative Q learning. You kind of think of it like capital a little bit. So that's kind of the fundamentals of reinforcement learning. Now, robotic foundation models, okay? Large-scale data sets plus self-supervised robotic algorithms and flexible models. This is the This is the sort of the holy grail, and he introduces a couple of papers, the ViNT paper, which I've discussed already, visual transformer. I think what I found really interesting is the paper on using video data to pre-train a robot. So the paper's name is Robot Offline RL from Internet Videos via Value Function Pre-Training. The idea is that you think of using humans, data from humans, okay? They do stuff, and you discretize the video, let's say in terms of frames, or you could discretize it also in terms of epochs. So that's an engineering question, but you discretize it and you create some sort of a reward design learning function. In this case, they use temporal difference learning, which means that you just say, okay, if I go from epoch 1 to epoch 2, do I get a better result or not? And you use the data set as a sort of baseline, so an offline reinforcement learning type baseline that then serves a robot to learn on that data set and improve its actions. The culmination of this is two other papers. RTX is the endeavor by Google to have diverse data sets for robots doing tasks, use video of robots doing stuff, and then use offline RL for pre-training robots and then fine-tune them. Q-transformer discretize actions in tokens and then use sequential decision-making algorithm. For example, RL methods to optimize actions. In the paper, they aim to combine large-scale robotic learning from diverse and real-world data sets with modern, high-capacity transformer-based policy architectures. Since transformers models use discrete token sequences, they convert Q-function estimation problem into a discrete token sequence modeling problem and devise suitable loss function for each token in the sequence. So discretize action space and then use self-attention positioning to combine and use Q learning. So in that sense, you don't predict the next token, what you predict is the next value that a certain token is assigned to. I think what's interesting, RL with generative models, is how can RL be used to improve diffusion models? Okay, this is, in my opinion, this is new. I've never heard this one before. So this is kind of subtle, but it's still important. So you have a diffusion model that can generate, for example, a dolphin riding a bike. But then you ask yourself, how can we get to the task even though we don't have that particular goal in the data distribution? This is the fundamental idea that Sergei puts down here. And I think, again, this is, of course, it gets to the same big picture problem, right? Which is we have data-driven generative AI, which is match data points to distributions, use statistical comparisons, and then we have RL, which is optimization. How can we combine those? Well, we could have a data set with dolphins and bikes, and then find RL, a trajectory where we combine that and have a dolphin riding a bike. Lastly, what Sergei talks about is RL with large language models. What he's suggesting here is, can we make large language models better by using RL? And he's specifically talking about RLHF, okay, reinforcement learning with human feedback, where he's questioning whether that's enough. And even Karpati this week at the Sequoia conference talked about this, and he even mentioned, he said it was silly to do it. There should be better ways to do it, and offline RL could be a way to do it. For example, you could generate billions and billions of conversations through synthetic data generated by LLMs, and then use them as a base for offline RL, and then use some sort of Q-learning to get to the trajectories which actually get you to better results. Now, my personal view of this is the question of whether offline RL is really so much better than reinforcement learning with human feedback gets to the question of safety. And I don't mean safety in a sort of Google way, which is a central ministry of ethics type planning, where all kinds of wokeism getting stuffed down the throat of the model. I'm talking general safety. For example, you could have a chatbot that suggests somebody asks a question and says, I'm not feeling well, what should I do? And the answer could be, well, you should just lock yourself up, because if you walk out in the street, you could get an infection or something like that. Like, the model could use machine psychology and offer it to human, and that's probably in most cases not such a good idea. So move 37 in principle could be a problem, because we might not want that. And that actually was shown in Davide Scaramuzza's presentation, because the drone did use a move 37 type move, but that kind of move by a human would have been suicidal. And it would have taken thousands and thousands of drones for a human to learn that. Or think about it this way. If you're in a ski race and you're going downhill 100 kilometers an hour, it might be more optimal for you to do a somersault in a curve and win a couple of tens of seconds. But you're going to do that. If you do that a million times, you might actually succeed and get through and master it, but you're going to die many times before. So it's not really a good idea for a human. There's also this problem that we encountered in the hedge fund world when we did special situations, which is a huge problem. And that is special situation. Most of finance is actually based on statistical analysis, computational methods. Everything is always, you look at it probabilistically. But when you look at special situations, by default, there is no probabilistic analysis, because the n is usually very little, 1. You look at a merger and you try to predict the probability of a merger going through. Well, each merger is very specific. You can't look, it's like a marriage, right? Yes, we have a statistical analysis of a marriage, but each marriage is still specific, and you can't make any kind of predictions whether a marriage will succeed, whether a merger will succeed, whether a merger will go through. So in that sense, we have to be very careful when we use machine psychology and apply it to real-world examples, because machines can die. Machines, particularly when they're trained in sim, they don't have a concept of risk. They don't have a fear. They don't have an embodied weakness that we humans have. They're not cold. They're not hungry. So we can't separate ourselves from that. And I think Davide Scaramuzza's example was very good. The human drone flyer could learn those maneuvers, but it would cost a lot, and that's part of the equation here. And I think when we talk reinforcement learning with human feedback, when we talk models, when we talk whether a chatbot can get good solutions, is that really what humans would want to do? Now, to Sergei's defense, he's saying, look, if I generate synthetic data with a large language model, by definition, the large language model was trained by humans putting data into the internet. So that is human behavior, and we're just going to learn more optimal trajectories within the context of human behavior. So in that sense, in that synthetic data set, you will not find move 37s, but then you're hoping to find a move 37. So how is that possible? Well, it's possible because you have emergent behavior. You have maybe like a sort of a Monte Carlo non-zero probability types, Harry Potter world situation. What I mean with that is, if you combine a lot of synthetic examples, and some of them might be absurd, but if they're non-zero and you are doing Q-learning today, and you have Monte Carlo search tree that you can go through, you might actually alter your behavior a little bit. So if there is a non-zero probability of a Harry Potter world, you might act differently today. which is reasonable. Think about, if you think about, I mean, your life today would be different if you knew that there is a non-zero probability of a nuclear war, that there's a non-zero probability of actually, that there's non-zero probability, but let's say let's say there's a non-zero probability of a Harry Potter type situation anytime in your lifetime. You probably would alter your actions today a little bit, just slightly. You might take a little bit more risk here, a little bit more less risk there. So that's the idea of Q learning and using RL. That's really the fundamental idea. If this is, I mean, think about, you could think about this also. What's the difference between, America and Europe? Well, America is the land of opportunities, right? What does that mean? Well, there's a non-zero opportunity, there's a non-zero probability, or there's a higher probability that you might, become Elon Musk in America than in Czechoslovakia or Czechia, excuse me. And therefore people act differently, even though most of us don't make it, right? We don't become billionaires. But because there's a slightly higher probability we change our behavior. This is what culture does. This is why supposedly people in California are somehow freer or more optimistic, right? Because somehow here people believe in impossible things, and they might believe in the same things over in New York and in Europe and in China, but maybe with a lower probability. So that's kind of the idea. I think that's where I see reinforcement learning with offline reinforcement learning. So to summarize, Sergei's talk, unbelievably pivotal, very, very important, because he's putting the thumb exactly where the action is. We have data-driven generative AI models, which are based on statistical inferences and variational inferences and all those things. And we have RL, which is an optimization solution to an optimization problem. How can we combine them? And if we combine them, we have a better chance of move 37, or we have a better chance of outcomes that are emergent. And the reason for that is because we combine a massive compressed knowledge database, which is the data distributions that we've learned in, let's say, a transformer-based model. We've learned where words belong and how they relate to each other. We've learned how image frames relate to each other. We've learned how tasks relate to image frames. But now, how about the trajectory? How about finding optimal trajectories? Well, that's a reinforcement learning problem. Combining those, we could get much better results. Thank you.